Cavity right here. That's the other vortex. Another picture of that cavity. There it is right here. This is exactly the shape of the right ventricle. It's a vortex that's been pushed off on the side by this heavy muscle. Okay, so I made it. I make everything. So I made this shape. And then this was the epoxy that I added on. This is the shape of the other vortex that's been pushed off to the side. Right out of the medical books that shows you this. There it is. They have no idea why the right ventricle has that shape. That's because this is the vortex. The blood comes in here and it swirls around right there and goes out the pulmonary arteries to the lungs. Now if this, here's the real heart. And there it is right there, without any blood. Now, if the heart was a pump, okay, it would have to have valves. There is a valve here and a valve here, and some people have problems with these valves, and they have to be removed. So that the right ventricle has no valves in this person, and yet the blood goes right to the lungs like they weren't even there. You can't have a pump without valves. That's streaming. Okay, so what's interesting about this is how interesting geometry is. For instance, I'm going to take this down. I'm going to just get rid of this, and I'm going to draw something else here for you. I have a little block here, but if I draw the top of this, this is what's interesting. I showed you this. If I draw the top of this, I'll do it right here. If I draw the top of this, this is what's interesting. I showed you this. If I draw the top of this, I'll do it right here. I got some new ones, don't I? If I draw the top of this, and I draw the middle of this, this is so fantastic. If I take a triangle, an equilateral triangle, and I draw a circle and an equilateral triangle, okay, and I draw another triangle into that, this triangle is actually 1 to 4. So there's 1, 2, 3, 4. So there's one triangle, and to make 4, you have to draw a circle around it. And then that's what's going on in here. You see, that's a triangle. And that circle right there is exactly half the size of this. So this ratio is 1 to 2. But it takes 4 of them, which is 1 to 4. Now I can't explain this a little bit more, but here's the deal. The red blood, if the blood is 100% in our body, 15% of the blood is red. 15%. There's 85% blue blood. You know, everybody, oh, it's half and half. 15 and 85. That's amazing. So, if you think about this, 15 to here, and then the blue blood would be probably still red, but anyway, this would be 85%, the 15%. Okay, here's the right ventricle I just showed you here. This holds 4% of the blood. The left ventricle holds 3%. 7. Okay, so if you look at the red, this is red blood, 3. If you take 3 away from 15, you get 12. The form has 12 edges. Now, what about this? This bothered me for a long time. What is going on here between 15% and 80? Well, here's what I did. I took, if you take a cube and you double it, that would mean this would be doubled. You have 4. Make sense? Okay, so this is, if this is 1, this is 2, isn't it? You know, this is 1 and there's 2, but really there are 4. Follow me? Okay, now I want to do that again. So I'm going to double this again. So I'll put 1, 2, 3, 4. So I'm doubling it. Oh, man, it's just right. So now this has 1, 2, 3, 4, and this has how many?
16.
How many?
16.
Okay, 16. Now, let's see if I can do this quicker. Okay, I can do it quicker. Now, what we've got here is we got the 1, and we got the, this is 1, this is 2, and this is 4. That's where I got to. Okay, and this is really 1. This is 1, and this is 4. There's 1 and 4. This is what you said, 16, right? Okay, so what should this be?
64.
It should be 8, right? 8. So there should be 8 divisions here. And how many in here?
60.
Yeah, 60. That's a lot in there. Okay, so 1, this is 3, 7. What is this? What does this add up to? 15. Now let's add up this. 1 and 4, that's 21 and what's 60? 85. Yeah, you see? Okay, who's behind all this?
God.
Yeah? Somebody's behind all that. I'm telling you, somebody's doing this to us.
Great geometry in the sky.
So what I figured out is that the ratio of 1 to 2 is a line. This is a line. And the ratio of 1 to 4 is planes. So this is a line, and these are planes. So think of it, huh? We have a distance. This is either a distance or a time, a speed. Okay? And this is flattening out the blood into a plane. And that's what happens is everything goes out, right? It spreads out into a plane. So whoever designed the heart figured this out. So it's very important to realize that this 1 to 4 ratio. Okay, so let me go into the internet and show you more that comes off what they have. These are doctors' ideas of how everything looks, and they don't know where it's coming from. But as you spin the form, you see that the sphere is exactly the same. Now, this is a drawing, this is a photograph of the top of the heart, okay? This is the right ventricle. This is the size of the blood that comes from the lungs and goes into this valve. It's called a mitral valve. And it's exactly 4 to 1. And it's exactly, this circle is exactly half the size of this circle. And this circle right here is exactly this size. Now, where this is divided into 2 is where all the energy is. Here, here, and here. That's the reason that you see a circle when I spin it. It's because you're seeing this, this, and this. And that's what causes that circle. Not out here, but inside. So that's where all the energy points are. So, if you look at the construction of the inside of the heart, okay, it should match this. And it does. The form inside the heart has a geometric form based also on 3. More organic and spinning. Okay, this ratio is to 1 to 4. All right, so here we go a little further here. It shows you these spinnings. It shows you this again, and it shows that cavity. Isn't that beautiful? Here's the form upside down. If you look at the heart from the bottom, it looks like this, and it represents that spiral. There's 2 vortexes, and they're both turning in opposite direction, just like my form in a vortex. Okay, so when I did this, okay, I realized that this form here, that form here is exactly the opposite of the one at the top. So what I decided to do is to take this form and put it inside this one and spin it again. Now remember that Platonic forms have never been put inside of others and spun. They've been put in there, but they're never spun. I also found out that if I take a tetrahedron and I put a little tetrahedron in exactly half the size, and I'll show you what I mean. So if this is the base of the little yellow triangle, and I want to open it up to make the size of the bottom triangle, I have 1, 2, 3, 4 again. 1 to 4. Okay, so that makes the size of the bigger one. So I know that this is the size of the little one. It's half exactly the size. Look, see the proportion again? If I draw a circle around here, 4 to 1. I found out that this is what's happening, is this warmth is opening up to air. And as it opens, it turns into this shape all the way up to the bottom. See if I have one separated. I do. This is the form that opens up all the way. This blue form is opened all the way up to the side. So the yellow has moved all the way to this corner. So this is an equilateral triangle. This is root 3. And you have 2 equilateral triangles on this. And as the tetrahedron starts to go in, okay, it goes from 2 to 1 to nothing, an edge. So here it is here, an edge only. And when this opens up until it gets to exactly 1/2, is the 7-sided form. It's right in the middle between 2 equilateral triangles and a line. And that happens to be right here. Here's the 7-sided form in the tetrahedron, exactly at the midpoint of opening this tetrahedron up. It's perfect shape. All right. So I put it inside each other. I put them inside like this. I took the one that was at the very end of this one, and I put it in the big one, which was at the top, and I put them together like this. That's this, with a little tetrahedron inside. And I spun it again. And this is what happened. I got this form. This is a 7-sided form, and now the form inside has changed. So I don't know if I have those handy. I did have them. I was going to show you. Anyway, I found out that this right here is the, in spinning, looks like this. So this is the inside form. And if I spin it, it looks like that. You see how it looks? Now remember that the heart spins. So I found out that when this goes on, that this is the thickness of the muscles in the heart. The distance between this one, okay, and the bell-shaped one, the distance between them is the distance and thickness of the heart. Now, the muscles of the heart. Now, I have to show you minimum surfaces because it's a little difficult to realize that here's the shape here. I'll show you this first. If I put this against the wall, see how this is flat? Here it is. It's like this, isn't it? But if I turn it like that, this becomes flat and this sticks out. See how that sticks out? Okay, look at this. This is what they're coming up with. It's the inside shape of the heart. And what's amazing is here, this is a casting inside the heart. This one is too, and it's straight, and it's straight. That's because of this. They think that this is two-dimensional. It's not. It's three-dimensional because at certain views it's like this. So I put this into minimum surfaces. Minimum surfaces is like I blow a bubble into a cube and it comes out organic. And this is what the 7-sided form looks like in a bubble. So if you take the 7-sided form and you put it into minimum surfaces, which is a bubble, it looks like that. So now we have an organic shape that's based on a lawful process based on minimum surfaces. Okay.